We're going to talk about polar coordinates, but before we can do that, we need to talk about rectangular coordinates. Now, rectangular coordinates are the way that we're used to thinking about the xy plane. We have x, y, and basically if we have a point here, let's call that point A, comma B. We have a couple different ways of getting to that position. You can think of it in terms of movement, so you go its distance of A in the x direction from the origin, a distance of B in the y direction, and that will get you that point. The other way we can think about this is as the intersection of two lines. You have the vertical line, x equals A, and the horizontal line, y equals B. And the intersection of those two lines gives us a single point. And this is why it's known as rectangular coordinates, is because when we look at the shape that we get when we draw these lines, is we get rectangles. And so that's why we have rectangular coordinates. And so this is the general idea we have for coordinate systems, is that we need to find coordinates. We need to find a way of describing different points on the plane. Now with polar coordinates, instead of thinking about rectangles, what we're actually doing is we're thinking about circles and angles. So here's the origin. Instead of thinking about the xy grid like this, what we're actually thinking about is we're first going to think about circles. And then we're going to think about lines emanating from the origin, like this. Now the important thing to recognize is that any point on the plane, let's just say this point right here, can be found as the intersection of a circle centered at the origin and some lines emanating from the origin. And so this one right here, it's whatever circle this is and whatever line that is. And so we need to find a way of describing this. And in order to do that, we're going to use two values, typically written r and theta. R right here stands for radius, and theta here is an angle. And if this feels familiar, it's because it kind of is. We've been talking about these sorts of things from the beginning of class. Every single point on the plane is on some circle centered at the origin at some angle in standard position. And so the formulas for this, I'll write down the formulas first and then we'll try to understand them. X is equal to r cosine theta and y equals r sine theta. And these should feel familiar because these are actually just a rearrangement of the definition of the original sine and cosine functions we started with. At the very beginning of class, we had cosine theta is equal to x over r, and sine of theta is equal to y over r. And so this representation in polar coordinates turns out to be related all the way back to the stuff we were talking at the beginning of the semester. Let me just do a picture down here. Right, we had a value r, had a value y, a value x, and then here's an angle theta. Right? And so this picture and these formulas all match together. And as we said, any point on the plane up here, so let's say that that's this point, it's on some circle of radius r and some angle theta in standard position. And so this is the connection that we have between polar coordinates, the formulas, the values, the ways we get to them, and these ideas from trigonometry that we've been carrying with us the entire semester. To convert between polar coordinates and rectangular coordinates, we have these formulas. So this is the formula to convert from polar coordinates to rectangular coordinates. You can see that if you give it an r and a theta, the output is the x and the y. And so x is equal to r cosine theta, y is equal to r sine theta. And again, that picture is just this picture right here. R is our radius, here's our angle theta. The x coordinate goes this way and the y coordinate goes this way. And this is just a restatement of the basic properties of the sine and cosine functions. For the other way around, if you knew x and y, you can get r and theta using these formulas. R is equal to the square root of x squared plus y squared. And the relationship for theta, we actually have to write it this way. Tangent theta is equal to y over x. The reason why we can't write theta equals inverse tangent of y over x is because the inverse tangent function will only give us values in the first and fourth quadrants. And so it doesn't quite give us the full relationship. You might be off by pi radians or 180 degrees because the angle itself is in the second or third quadrant. And this actually is the same picture. So r is equal to x squared of x squared plus y squared. That's the Pythagorean theorem. Tangent theta equals y over x. Tangent is opposite over adjacent. And so this picture actually relates both of these together. Here are two examples of converting between polar and rectangular coordinates. convert negative 3 root 3 comma 3 from Cartesian coordinates to polar coordinates. Now we're starting in Cartesian coordinates, so let's draw that picture. Negative 3 root 3 comma 3, so negative 3 root 3, and then 3 up. We draw our triangle, right? So there is our reference angle, and here is our angle theta. Right, so what do we need? If we're trying to convert to polar coordinates, we're going to need a value of r and a value of theta. So here's theta, and r is, of course, the length of that part. So we can start with r. Now, if we just looked at the formula would tell us that r is equal to square root of x squared plus y squared. But if we just look at the picture, it's the Pythagorean theorem. And so it's often easier to just draw the picture and use the picture to guide you rather than trying to pull formulas out of the top of your head. So square root of x squared plus y squared, which is, let's see, the x squared, so that's 3 root 3 squared, so the 3 squared is 9, and the root 3 squared is 9 times 3 is 27, plus 3 squared is 9. 27 plus 9 is 36, root 36 is 6. So our r value is equal to 6. Then we need to figure out theta. Now there's a little bit more going on here. Let's call that rho for a moment. We can think of this in terms of the geometric triangle here, and then figure out what rho is based on this triangle. Or we can think about all the other, the graph of the tangent function and recognizing this is in the second quadrant and using the inverse tangent and all the sort of stuff that we'd have to do if we went straight to the formula instead. I'm going to just go ahead and go with the geometry, and we'll see again how the tangent formula sort of spills out of this. So we have a value of rho, and we need to figure out what rho is. Now we have a right triangle here, and so we have any of the trigonometric functions we want to use, sine, cosine, or tangent. All of them can be used here to figure out this geometric angle right here. I'm just going to go with the tangent function because that's the typical one. So tangent of rho. So tangent is opposite over adjacent, and remember that we're thinking about the geometric formula, the geometric triangle here. So this will be a positive. So opposite is 3 over 3 root 3, which is 1 over root 3. And that tells us that our reference angle rho. Now, you may or may not have the tangent values memorized. You should be able to work it out from the sine and cosine values, but this is actually one of the known values. This one turns out to be rho is equal to pi over 6. Now, if you weren't sure about this, you could always rewrite this in terms of sine and cosine and try it again, and you'll recognize those values a little more easily. Anyway, we have rho is equal to pi over 6, but what does that mean theta is equal to? Well, theta is going to be pi minus pi over 6. Which is going to be 5 pi over 6. And so in polar coordinates, this point has an r value of 6 and an angle of 5 pi over 6. And so that's how we get the first one. For the second one, convert 2 comma 7 pi over 6 from polar coordinates to Cartesian coordinates. Once again, we'll use the picture to guide us. 7 pi over 6. So 7 pi over 6 is just a little bit bigger than pi, so it's going to be down here in the third quadrant. And we have a radius of 2. Right, so again, once again, we can start thinking about our reference angles here. So that reference angle would be pi over 6. And we can do all of our calculations based on the signs of everything that we know. So the x-coordinate is negative, the y-coordinate is negative. So x equals negative 2 times cosine pi over 6. And y is equal to negative 2 times sine pi over 6. And this is using this triangle picture right here and just using the basic geometry. If you wanted to use the formulas, you would actually just do the radius is 2, and you have to calculate cosine of 7 pi over 6 and sine of 7 pi over 6. And when you go through this calculation, when you do cosine 7 pi over 6 and sine 7 pi over 6, you're going to have to adjust the signs as they are over here because, again, you're in the third quadrant, so you know the x-coordinate is negative and the y-coordinate is negative, which means that sine and cosine are both negative. And so both of these approaches work. It really doesn't matter which way you do it. You just need to do the calculation. And I didn't leave myself enough space on the right, so cosine of pi over 6. Cosine of pi over 6 is root 3 over 2 times the negative 2 is going to be negative root 3. Sine of pi over 6. Sine of pi over 6 is going to be 1/2. So negative 2 times 1/2 is y equals negative 1. And so the coordinate is negative root 3 comma negative 1. And so for both of these, as long as you understand the picture, the rest of it should follow from all of your previous experience with trigonometry.